Okay. Question about how to linearize an exponential function. Okay, so let's just take an example. Y equals 5 times 1.4 to the x. We want to linearize this. Now, in general, if you have a graph of log y versus x, we've seen already that if that graph is a straight line, then y is an exponential function of x. So you can review that in the preceding class. And similarly, if log y versus log x is linear, then y is a power function of x. Okay, so this has already been established. But let's now see what happens if we do log y versus x for a function that we know is exponential. We've already said that if you get a straight line graph, then of log y versus x, then y is an exponential function of x. We never said that if y is an exponential function of x, then log y versus x has to be a straight line. So let's see. But if this is the case, and we suspect that it is because of this, then this is to linearize this function. We just graph log y versus x. Okay, so to linearize this exponential function, it's going to turn out that works. We find first log of y. Well, log of y is the log of 5 times 1.4 to the x. Then we just apply the rules for logarithms. That's going to be the log of 5 plus the log of 1.4 to the x, because a log of a product is the sum of the logs. And then a log of a power is the power times the log. So that log of 1.4 to the x is x log 1.4. Now look at what we've got. Log of y equals a numerical multiple of x plus another number. That's the form mx, y equals mx plus b. I've written it out again with the log of 1.4 in front of the x. And we see that log of y is log of 5 plus the log of 1.4 times x. And that's the form mx plus b, where here's your mx term. M is your log of 1.4. And you have plus a log 5, that's your b. That's mx plus b with m equal this, b equals this. So this linearizes the log function. It's quite straightforward, as long as you remember the rules. But until you've done it a few times, it's going to seem unfamiliar and a little weird. Okay, now, making sure that I'm not in the way of the board here, or the camera. We have some y versus x data. We just start with this data, and we're going to linearize it. Okay, so what we do is we do a log of y, because of course if the data is exponential, and actually what we're doing is we're testing to see if this data is exponential. Okay, we can do any log of y versus x and see if that gives us a straight line graph. If it does, then we can get an exponential model for the data. Now, all these numbers here are give or take a tenth, I think. I did them all by mental estimation, and I explained a little bit about how I kind of do mental estimations here. You got to visualize the curve, so you got to be familiar with the curve of an exponential function, the curve of a logarithmic function, and it's not a necessary skill. I'm not going to test you on it, but it's a very useful skill for looking at graphs and understanding graphs. Okay, so anyhow, I made these estimates. And of course you can take a calculator and you get the results. You can even take a calculator and tell it to do an exponential fit, which has no benefit whatsoever except you get the right answer. You don't learn anything by just doing that. So we want to do this. We want to do the log base 2. And I use log base 2 because that's easy to estimate. Okay, I know the powers of 2, and I can interpolate between powers of 2. Okay, so anyhow, they're the logs, estimates. And another reason for the estimates is you're going to see how robust this process is. And ignore the stuff in orange for right now. So here's a graph of our actual data. It looks kind of exponential. Since it looks kind of exponential, we go ahead and we do the log thing. And then we graph the log of y versus x. That's here. And that's easily done. And when we do that, we see that these points appear to lie very close to a straight line. And remember that these are ballpark estimates, not really ballpark, but they're estimates with a potential error, and you still get something very close to a straight line. And I didn't fudge that. I honestly located these points, and then I drew a straight line that more or less fits them. Okay, so having done that, well, we do as we did in a previous class. We get the equation of the straight line. To get the equation of a straight line, you take 2 points on the line. Or you can take the y-intercept and a slope. But in any case, I took 2 points in the straight line, 7, 12.2. And that's just, again, an honest estimate. Now, this isn't a data point, and I probably should have used a different color here to indicate this point is not like these. These are points that we get from our data. They aren't actually data points. These are data points. These are transformed data points, transformed by doing the log. Okay, down here we do, we estimate the y-intercept at 0, 8.7. And again, okay, the 0, 8.7 is an estimate from the graph. Now, we have these 2 points. We can get the straight line through the 2 points. And just looking where everything is. Straight line through this point and this point. Well, we first find the slope. Rise divided by run, 3.5 over 7, which is it's not 0.7. 7 goes into 35 5 times. 5 goes into 35 7 times. So everything I did up there is not totally accurate, although the steps are correct. Let's go ahead and fix that. It's not too hard to fix. Okay, so that should be 0.5. So when I come up here, this should be 0.5. So all my 0.7s need to become 0.5s. And that's going to change one of my numbers down here, as we'll see. Okay, so that should be 0.5. This should be 0.5. This should be 0.5. This should be 0.5. Okay? And then this number is going to be different. Okay, so anyhow, here's 0.5. That's the slope of our straight line. And the straight line is, in slope-intercept form, slope times x plus the y-intercept being 8.7. So, now whether you use the y-intercept in another point, whether the way you get the straight line, there are various ways you can do it. I don't care which way you do it. But make sure that the 2 points you use to make these estimates are fairly far apart. Because if they're too close together, then little tiny errors in your estimate are going to have a huge effect. Okay. Or they're going to tend to have a huge effect. You might luck out and they don't, but it probably will. So, now we see that this is a straight line of log base 2y versus x. So that instead of saying y equals mx plus b, it's log of y equals mx plus b. Okay. So log base 2 of y is 0.5x plus 8.7. And remember, I'm using log base 2 because it's convenient to estimate. Your calculator probably doesn't have a log base 2. This all works just as well if you're using a calculator, if you use either the natural log or the log log. Okay. Any log is going to work. And I'll explain a little bit about why in a minute. Okay, so log base 2 of y equals this. There's your straight line. So you raise 2 to the power of each side. 2 raised to the log base 2 of y should then equal 2 raised to the 0.5x plus 8.7. Okay, then 2 to the 0.5x plus 8.7 is just 2 to the 0.5x multiplied by 2 to the 8.7. And that's going to be, well, 2 to the 0.5x is 2 raised to the 0.5 power raised to the x power by the power of the power rule for exponents. Then I estimated that 2 to the 8.7 is 400. And originally I estimated 2 to the 0.7 to be 1.63. I think that's probably not a bad estimate, but you never know. But this would actually be about 1.4. 2 to the 0.5 is 1.414, and then some more decimal places. But nothing that we've done justifies more than just a plain old 1.4 here. Okay, nothing is accurate enough to go to a 1.41 even. But we'll just push a little bit and go to 1.41. We're not going to go to 1.414. That would require a whole lot of precision and a whole lot of linearity in this graph. If the graph isn't almost perfectly linear, there's no justification for going any further with the decimal points in this number. Okay, and 2 to the 8.7 I think I estimated to be 400. It's just based on 2 to the 8th is 256, 2 to the 9th is 512, and the curvature of the exponential graph tells me that 400 might not be a terrible estimate, although give or take maybe 20. Okay, so anyhow, now we have our function y. Okay, so where is my red chalk? Yeah, I'll grab a piece over here. So all this has led us to this model, which I could write without the intermediate step now. Y equals 400 plus 1.41 raised to the x. Just another exponential function with a number out here and some number to the x power. I then did the problem that actually appeared on somebody's homework. Okay, and the number here was 860, not 726. Number here was 2200, not 2865. I ignored the numbers in between, kind of assuming that we'd have pretty much a straight line. And I just made some estimates that the log of 860 is about 9.6, base 2 log, 9.6. The base 2 log of 2200 is 11.1, which is consistent with this and with this and this. In other words, the log of 860 should be between the log of 726 and 936. So if this is 9.4 and this is 9.8, that should be 9.6, maybe 9.7, and maybe I'm still off. We'll see. But anyhow, if you have this, and then 2200 is pretty close to 2138. Not so much, not so far that if 11.1 is good here, it's going to be good here. I did that. I found the slope. In other words, I ran through all this with this information, and I got a slope of 0.25, and that's nice because 2 to the 0.25 is pretty easy to do. And it's a little less than 1.2 because 1.2 squared is 1.44. And so 2 to the 0.25 is, well, it's the square root of the square root of 2, and so forth. You don't need to follow all that. But we've got 1.19 here, where here we got 1.41. And then 2 to the 9.4 is about 720. And where did I get 9.4? We conjecture that the log base 2 of the y-intercept of the function that we get here would be about 9.4 if we did the graph. Okay, and yeah, I waved my hands over that a little bit, but you don't have to follow it. Just what I'm illustrating here is that even if you do this in your head, you get pretty accurate stuff, if you're fairly good at doing things in your head. Okay, well 2 to the 9.4 is about 720 because that kind of matches what I estimated up here. And as a result, our model is 720 times 1.19 to the x. Then I said something about a calculator. It's been a couple of days since I did this. I don't know why I mentioned a calculator. But just that you could use a calculator to get a better result, I think. The answer given in the book then for the data was 702 times 1.21 to the x, or the answer given in the homework, which is very close to the estimates. Again, just showing that these estimates are pretty robust if you have pretty good exponential data. I did comment on interpolation. I don't remember the details. I was commenting on the upward concavity of the graph, but that's not particularly important right now. If you want me to talk more about interpolation with nonlinear functions, I'll be glad to do it. Just ask.